Okay, here is a handout. So, take one down, pass it around. It's half. Okay. First, I have to try to split it into some equal sizes. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Everybody here but Jasmine.
Oh, thank you.
Okay. Today we're going to look at the Maxwell-Boltzmann distribution to understand how things like the most probable speed, the average speed, and the RMS speeds are calculated. So I have here, and I know this looks a little bit different than what I had on the slide. Yeah, you got a question? Ask Cody. The equation looks a little different just because I put F as a parenthesis of V instead of, I think it's PR as parenthesis V that I had in class yesterday. But this here is called the Maxwell-Boltzmann distribution. It's an equation that was developed by using statistics. So it's purely statistics, and we're not going into the statistics of how they did it. But we want to see how that plays out. The important thing to understand about that problem or about that equation is it's telling us the probability of having different speeds. And in fact, the probability of speed between V and V plus dV is what that equation really is. That's equal to F of V dV. You always have to actually do it that way. It's the probability of being within a range, because if you have a continuous distribution, I mentioned this in class yesterday, the probability of having an exact value is vanishingly small, right? Probability of being between a speed of 300 meters per second and 300 plus 0.000001. Wait. Jasmine is here. You should have said something when I said everyone but Jasmine.
Oh, sorry, I didn't.
I had you marked as not here and him marked as here. Fixed it now, thankfully. Okay. So the chances of that particle having value between 300 and 300 plus 1 billionth meters per second, that's a reasonable number if you have somewhere in the ballpark of 10 to the 26th molecules. But if you make it smaller and smaller and smaller, so 1 part in a billion to 1 part in a trillion to 1 part in, the smaller you make that dV, the smaller and smaller you're going to have the probability, until if you say at this exact value of 300 meters per second, probability of having exactly 300 meters per second is 0. Probability of being really close, well, that's reasonable. But exactly 0, not. So when we're doing a calculation, we have to say the probability of being between this range is given by this equation times dV, that infinitesimal little width. So that's how we're going to use this. Now, we're going to do a few things here. Things to note about that Maxwell-Boltzmann distribution are limits. Being at rest is 0. Look at the equation. If V is equal to 0, then you're going to have times 4 pi times 0 squared e to the minus 1/2 m 0 squared over kt. So that exponential is e to the 0. What's the value of e to the 0? 1. So that's going to be a 1 for this piece right here. But then this here is multiplied by 0. So 0 times 1 is 0. So the probability of having a speed of 0 is 0. You can't have a particle at rest, according to this. You can get vanishingly close to at rest, but you can't have it at 0. Now go to the other extreme. What if I'm going to try to move something and not mess up. Excellent. So what if we go to the other extreme and we say, what's the probability of having an infinite speed? Now, if you look at this and you do the same breakdown, this here is, of course, infinite. And this here, what's e to the minus infinity? 0. So that's infinity times 0. 0 times 1 was easy. 0 times 1 was 0. Infinity times 0, it's undefined. It's indeterminate. So what we're going to do in a case like this is essentially the same thing we did before. We use L'Hopital's rule. Now, by the end of today, you're just going to believe L'Hopital's rule always gives you 0. Because when you do this, L'Hopital's rule gives you 0. How does it give you 0? Well, just think about it this way. Actually, maybe it'd be quicker for me to do it here than where I planned on doing it. I'll do it here, and then when we get to where I planned on doing it, I'll say, and as you saw from before, a polynomial times an exponential gives you, because that's what we have here, a polynomial times an exponential. When you take higher levels of physics, you learn about higher levels of infinity. And one of those rules you learn is that an exponential is an infinite polynomial. And since an exponential is an infinite polynomial, then it's a higher order of infinity. And so when I look at this, my physics brain says I have my x squared, that's a polynomial, what do they call it, rank 2 or order 2? I don't remember the rank or order. Times my exponential, which is of infinite order. The exponential one is the one that's going to dominate. And so I take that and I say, well, the value of the exponential is 0, and hence, when I use L'Hopital's rule, since that one goes to 0, it's going to be 0. But we can actually show it with L'Hopital's rule here. So let's do the limit as v approaches infinity of, and what we had was v squared e to the minus, I'm just going to put a for the constant part, v squared. Right? That's what we had. And so using L'Hopital's rule, you have to put it in the form of a ratio. And so I'm just going to make it as limit as v approaches infinity of v squared over e to the minus av squared. Not minus, plus, because I moved it to the bottom. So now v squared as v approaches infinity, that's infinite. E to the av squared as v approaches infinity, that's infinite. It's infinity over infinity. So using L'Hopital's rule, what's the next step? Take the derivatives of the top and the bottom. So the derivative of the top, 2v. That was tough. Derivative of the bottom, 2av e to the av. Squared. Thank you. Man, I don't mean to make mistakes, just for the record. So now I can look at this. I'll cancel the 2's. I'll cancel the v's. This is equal to the limit as v approaches infinity of 1 over a e to the av squared. V only appears one place here. Right? That's why this was easier than where I was planning on doing it. And so if I put in infinite for v, I'm going to have limit of 1 over infinity, which is 0. And so here's a quick application of L'Hopital's rule to give you 0. The way I was going to have before would have been a recursive method, much harder. So I'm glad I did it here. So this limit at infinity as well as the limit in 0 is 0. You can't have a particle going faster than infinity. You can't have a particle going slower than 0. Kind of makes sense, right? It's actually a little more complicated if you want to be relativistic about things. This is assuming speeds well below the speed of light. If you get speeds closer to the speed of light, you actually have to have a different form for the Maxwell-Boltzmann distribution. But for our everyday room temperatures, the speeds of the particles are not approaching the speed of light, and we can use this equation. So just pointing out that there is a relativistic version, because the true maximum speed particle can approach is 2.99792458 meters per second. And so the upper limit is actually probability is 0 at that number when you have the relativistic correct equation. Here are the things we're going to do with this. We're going to find the sum of the probabilities. Then we're going to find the most likely speed, the average speed, and the RMS speed. So first, the sum of the probabilities. If I have a probability function, how do I find the sum of all the probabilities? I integrate. So the sum of the probabilities is just going to be integral of f of v dv. Now I'm going to go to the next slide because I should have just made one more slide of this. I made 4 or 5 identical slides, but I didn't make one for the first part. So here's my f of v function at the top, and I am going to substitute b, which is just a constant here, and a constant here to make it easier to write. So that means I'm going to have that just because it's shorter. So coming back to this here, if I'm going to integrate, this over all possible speeds, what's the slowest speed possible? And what's the highest speed possible? Infinity in the non-relativistic approximation that we're using. That's what I'm looking for. So that's the sum of probabilities. What should the sum of probabilities probably add up to? What? You say 100? Let's say I have probability of me being in my office is 25%. Probability of me being in the classroom is 25%. Probability of me being at Breda is 25%. Probability of me being at Da Vinci's is? 5%. How'd you get that? Yeah. The probability, if you take all of the options, it should come to a probability of 100%. Or a probability of 1 if you're not doing percents. So this should come to, the sum of the probability should be 1. Probability of 1 means there's a 100% chance of the particle existing somewhere at some speed. So that's what it should be. So we're going to test against that. So how many people here feel comfortable doing that integral? Really? No. If it was v instead of v squared, then integration by parts would boom, you'd be there. But that v squared e to the minus av squared is kind of tough, and that's why I handed out this paper to you. This paper goes through the integrals that you use here with the Gaussian, Maxwell-Boltzmann distribution. And so it starts off by saying we want to find a generalized integral. They just drop off the b part because that's a constant. For, and I think it has x instead of v, so x squared e to the minus ax squared dx, going from 0 to infinity. Yes?
Why is it x to the n, though?
Okay, why is it x to the n? Because right now we're doing x squared. But if we want to find the average speed, we're going to do a weighted mean. Our weighting factors, our probabilities, our weighting factor is going to have v squared e to the minus ax, av squared dv. But then we have v times that weighting factor, so v times my weighting factor will give me a v to the third power. And so we're also going to have to do this integral with x cubed. And then if I want to find the RMS, I'm going to find the average of the speed squared, so I'm going to have v squared times the function, so I'm going to have to the fourth power. So we're going to be doing this integral for n equals 2, 3, and 4. And so that's why it has just x to the n. Question?
Will this be available on our exam sheet?
On the exam sheet, I'll give you the equations in the box.
Okay.
Not the rest of it.
Gotcha.
I mean, the rest of it wouldn't really help you if you had the equations in the box, because the rest of it is explaining how you do it. So as you can see, the first step was to do an integration by parts, exactly what Aaron had said. And when you do that integration by parts, you only have one integral. I didn't put it up here I didn't put it on my presentation, but if you have integral of x squared e to the minus ax squared dx, and you want to break into parts, you want the parts to be things you can easily integrate. You know what I can't easily integrate? E to the minus ax squared dx. So I'm not going to make my dv be e to the minus ax squared dx, because I can't integrate that easily. But as we were saying when I was talking with Aaron, if I put a v out front, then I can integrate it easily. Or an x here, I think that's why they used x instead of v, so we can use the normal. So I'm going to let u equal just x, and dv equal x e to the minus ax squared dx. Because I can integrate that dv. So let's do these two pieces. The first one, of course, is super simple. If u is equal to x, then du is equal to dx. That's real simple, right? We're all on that page. For the second one, I'm actually going to take this and say, oh, come on, scroll. And say, how would I do that integral? I would do that integral with the u substitution. Well, I'm going to call it w substitution here so I don't duplicate u. So I'm going to say, let w equal ax squared. So dw is equal to 2ax dx. And so that gives me my dv is equal to, notice x dx is equal to dw over 2a. So dw over 2a e to the minus w. That's something that I could integrate. I can integrate this to have v is equal to the integral well, if you do that integral, you just have to change the sign, basically. So that's my v. My v is minus e to the minus ax squared over 2a. Now going back to the integration by parts, and I'm going to have this integral is equal to, remember integration by parts, it's uv with my limits minus the integral of v du with my limits. So substituting in, that's going to be x times minus e to the minus ax squared over 2a from 0 to infinity minus the integral from 0 to infinity of minus e to the minus ax squared over 2a. And if I do this, what do I have? This first one has an x, a polynomial, times an exponential. Putting in the values of 0, I have 0 times, if x is 0, 0 times e to the minus 0, 0 times 1, that's just 0. If I put in the infinity, it's infinity times e to the minus infinity. It's infinity times 0. So that's where I have to use the L'Hopital's rule. And as we just saw, the polynomial one is going to lose to the exponential. And so it's going to be 0 for both terms in the first one. And I'm just left with this piece right here. And now when I get to this part, I notice that I did differently than what your sheet has. And I'm going to quickly scribble the differences. For your sheet, instead of 2, it used n, right? And so that means that this is going to be dv is x to the n minus 1, or excuse me, no, that's just x still. This one here is x to the n minus 1. So I'm going to have u times dv still has to give me x to the n, but I took one n away from the u, so that's x to the n minus 1, to put it in the dv. And so when I did my derivative, the du is going to have times x to the n minus 2 times n minus 1. Those two terms come from having n not equal to 2. And so if I had come to this final situation, I would have just had x raised to a higher power here, but still a polynomial, and then n plus 1 or n minus 1 doesn't matter. And over here, I would have had the n minus 1 and x to the n minus 2. And so that's why their answer has, for this second term, this term that I came up with was I to the 0 divided by 2a. But what is in your worksheet, because of having the n minus 1 there, you have n minus 1 multiplied by it, and it's, instead of I to the 0, it's I to n minus 2. So you have those changes. I should have remembered to put n in there, and then we would have had it come out. But I didn't want to do the whole problem again just for that. So we have there's all the corrections made now. So what does that do? That integration by parts simply shows that there is a recursive relation that skips a level. You can go from I, if you know I1, you can calculate I3 and I5 and I7 and I9. Well, yeah. If you know I0, you can calculate I2, I4, I6, I8. So we have to determine what I0 and I1 are. I1, once again, going back to our interaction with Aaron, that one we can easily do integration by parts. And so the I1 is calculated very quickly for you. I didn't even bring that sheet. But the I1 is calculated very quickly for you to give you a value. So what is that value for I1? It's what?
1 over 2a.
And then I2 took a lot more work, because for that I2, there's not an easy solution. And so their trick was to say, well, if I take, well, actually not I2, they did I0, didn't they? I0. I didn't write anything down. For the I0, you don't have any x times. It's just the integral of e to the minus ax squared dx from 0 to infinity. He said, well, let's try taking I0 times I0. Let's see what that gives us. Who comes up with this? Not somebody who's randomly throwing darts, but somebody who starts to see something that looks similar to something else. And so they take I0 times I0. On the left side, you have I0 squared, right? That's the top right-hand column of your page. And then on the other side, you have equals, and they put the integral twice. So that x is not a cross product. It's just a multiplication sign, because they're not vectors, right? It'd be vectors for cross product. What's different about the two integrals? Well, one's a function of x and one's a function of y. Why did they do that? Because they want to combine them together to make a more complicated integral. But they're not going to be the same variable. They're two separate integrals. And so they just use separate variables so they could combine them. And then they combined them and they said, why this looks like polar coordinates. like r squared is equal to x squared plus y squared. And when you have polar coordinates, you have, instead of having, dx dy, you have what is it? dr sine theta or something like that. I don't know. You integrate about the thetas because there's no theta here, and that gives you, oh, and I've got the r. It's r dr sine theta, or d theta. I think that's what it is. You integrate around the circle. No, that's not how the sine theta, now I think about it. It's just r dr d theta. That's what it is. So they replace dx dy with r dr d theta, and then they integrate the d theta to get 2 pi, and then they have an integral of 2 pi r e to the minus ar squared dr. Well, that is doable. That once again has r to the first power out front, and then an exponential with r squared. That's easy to do. And so then they do that calculation to find what I0 squared is, and then they square root it to find I0. So from all of that work, which you have laid out before you and I do not, I0 is equal to what? 1/2 square root of what?
Pi over A.
Pi over A. So we have those two starting values, and then the final I to any n is equal to I n minus 2 times n minus 1 over 2a. I got the last one correct, didn't I? Okay. So those are what we're going to use to calculate all of our integrals for this. So we're not going to actually do the integrals. We had to understand some calculus to understand where those equations came from. And, if this comes on the test, which there's a reasonable chance you'll have to do something like this, maybe find, the average of the speed cubed or the speed fourth or something like that. So if you have to do this, you'll just have the equations in the box. You won't have to go through the derivations, but you'll have to know how to use those and how to work it, right? Because there is calculus involved here, even though we're breaking it down to more algebraic forms. So all of this said, what was I trying to do? The sum of the probabilities, doing the integral. What is the n value for this integral? 2, because n was the exponent. So I'm going to have here that this is equal to I sub 2 multiplied by b. Why multiplied by b? Because I had that constant b in front of it. Right, this b right here. So I sub 2 is going to be I sub 0 times 2 minus 1 over 2a, and then times b. Well, now I have to look at what I0 is, and of course I don't have room up here, so going to the bottom. That's what I wrote, right? Oh, okay. B, did I have B? B, I0, 2 minus 1, 2a. So now I just have to put in my B, my I0, and my A. So I'm going to have two minus 1 is 1, so I'm dropping that off. Does that look right? Wrong right. Well, I stepped to my left, but what's the correct right? So now I just have to put in my values for B and A. So B was this cube root thing. I'm going to actually put it here. right? And these are, I see my writing here is rather confusing. So let's just go with what we have here. So B is going to be A is equal to there I've put everything in. And then we have to look at how we can simplify this. Well, if you look at things, that pi is the only thing different between these two pieces. So they almost cancel. And suddenly I fear, could I have made a mistake? That's impossible. And yet it seemed likely that I did. Equals. I got 1 over 4 pi. Where did I make a mistake? Somewhere I made a mistake because obviously it's supposed to be equal to 1. Is everything, can you guys double check for me? Is everything correct in this box? I had B, just doing this integral right here, it's going to be B times I2. And so I think, yes, here's the problem. B goes all the way out to there. B goes all the way out to there. I forgot the 4 pi in B, which, of course, adds a 4 pi on top. I was feeling a little bit wrong. So, through making a mistake here and there, we finally got to the conclusion that, hey, this equation is at least legit in that it says that the sum of the probabilities has to be 1. Now for part 2. What's the most probable speed? If I have this function for probabilities, how do I find the most probable?
Max.
It's the max, and how do we find the max?
No, sorry. Do the derivative. First 10 seconds.
Well, we really only need to do the first because we're going to have a value here, and the one that's correct. So we'll take the one that's not 0 or infinity. But normally he's correct. You do the second derivative to make sure if it's a minimum or a maximum.
If we didn't know what the graph looked like.
Yeah, if we didn't know what the graph looked like, then we would do that. So I'm going to find V where df dv equals 0. So just looking at the left side here, df dv, what rule do I have to use to take this derivative? I heard somebody say the product rule. I couldn't tell what you said, so I have to use the product rule. Everything has a b, so I'm going to factor out the b. Taking the derivative of the first one, that's a 2v. I can't write a 2 today. 2v. And then the second one, e to the minus av squared. And then the first one times the derivative of the second one, which is going to be minus 2av, e to the minus av squared. I know, I copied over into the next one. So there's my derivative, and I want to set that equal to 0. I'm going to factor differently. Everything has a 2, well, it does have a 2. Everything has a 2. Everything has a b. Everything has a v. And everything has an ea to the minus v squared. So if I factor as much as I can, b 2v e to the minus av squared, and that leaves me with 1 minus a. Just to make sure you followed. Oh, a, yes, I forgot this v squared. Okay, that's what I was going to go through to make sure you followed that I'd done everything right, and I didn't do everything right. So this v squared and this a are those two terms, and then I factored out everything that was in the first one, so that's why it is just a 1. And so all of that is equal to 0. What conditions will set this equal to 0 in terms of v? What values of v would set it equal to 0? Okay, so the first one, v equals 0. What's our next one? What is v going to be equal to make that one 0? If v is equal to infinity, plus or minus infinity, but we're only allowed positives. So those first two were the trivial ones that we're not going to use. We know that a speed of 0 is not going to be our most probable because the probability is 0 there. We know a speed of infinity is not going to be our most probable because it's a probability of 0 again. So it has to be the last one. So what condition do I get from the last one? I heard somebody say v is the square root of 1 over a. And so now we just substitute in what 1 over a is. The square root of, since a is m over 2kt, invert that 2kt over m. So that gives us v probable, the most probable speed, is the square root of 2kt divided by m. Now in class yesterday, I gave you a relationship between VRMS and this, but we didn't actually calculate what this was. Now we're able to calculate the most probable speed. And of all of our calculations today, that's by far the easiest. It was just a derivative and then algebra. Any questions about how I found the most probable speed? Okay then, no questions. Let's go to the next one. Oh, hey, look, here's total probability. I have them out of order. Well, we've already done this one, so average speed. To find the average speed, I now need to use a weighted factor. My average speed, in physics, we put that like this. When we take quantum mechanics, instead of calling it the average speed, we'll call it the expectation value for the speed. Expectation value means if I took a large number of samples and took the average of it, this is what I would get. In other words, it's the average value. So to calculate this average value or expectation value, I need to do the probability multiplied by the actual speed. So I have the speed multiplied by its probability, because that probability is the weighting factor. And then I have to add it up over all possible speeds. How do we add this up over all possible speeds? Integrate. My limit 0 to infinity. So that's going to be the integral from 0 to infinity. I'm going to put the b outside of my integral now. I have v times v squared, so that's v cubed. We've done all the calculus we're going to do. What should I do at this point?
So then I1.
I'm going to substitute in. This right here is the definition of I3. So V is equal to that constant B times I3. Here is what I had not paid attention to before. My B is equal to all of, I wrote this out to make our calculations quicker. All of that is B, and that's exactly equal to all of this, which is exactly equal to all of this. So those are three different forms for B that might be easier to use. Yeah.
Why are we multiplying function by b?
Because B was part of my f of V. Right. If you look up at the top line on the left, you have f of V equals, right below it equals B times V squared e to the minus AB squared.
But why are we multiplying that by b for average speed?
Because my integral is integral of V times f of V, and the integrals that we defined did not have the B in them. Right, the integrals that's on that sheet of paper you have don't have the B in them.
Yes.
And so I factored the outside of the integral.
No. What I'm
I must be missing the question.
Okay, so you've got average b, that's your first.
Yes.
It's going to equal integral. Why is it v times f of v?
Oh, why is, I thought you were saying V this entire time.
V.
Why is it V? Because we're taking the value of this, we want to find the average of the speed. I'm going to go all the way back and put this in very simple layman's terms. Let's say we have an exam. And on the exam, I have scores of, and I'm only going to have 3 scores in this exam. 1, 2, and 3. And looking at all the students, I had 2/12 that got a score of 1. And I had 4/12 that got a score of 2. And I had 6/12 that got a score of 3. So this is my, I'm going to put V because that's the unit, the variable we're using. And this is my probability function, which was f of V dV actually. So probability. If I want to find the average score, how would you find the average score based on this data?
Multiply each one by b.
I would multiply each value of V. So I would take 1 multiplied by its probability times 2/12 and add them up. And that would give me my average value on the test. And so we had weighting factors, right? These probabilities are the weighting factors. So I have the value times its probability times its weighting factor. And I have to add them up. Now, if it's calculus, replace plus with an integral, right? So instead of having this plus this plus this, we have the integral of my value, V, times the weighting factor, which was the f of V dV. And so in the equation I wrote, this is the value, and this here is the weighting factor. And then I'm adding them up over all possible values. That's a really key point. a huge reason I'm covering this now is so second semester when we get to quantum mechanics and we do exactly the same thing, we can look back at this and say, yeah, I understand how to do a weighted average. And so I can find what we call in quantum mechanics the expectation value, and we'll do exactly the same type of calculations. But when you get to quantum mechanics, things are a lot fuzzier, and it's good to have something solid you can look back on that you understood how it worked. So that's why we're spending all the time on this today. Okay, so coming back to this, the black, I had my expectation value was B multiplied by I3. I'm not going to put in my value for B until I determine what I3 is. I3 is going to be equal to I1 times 3 minus 1 over 2A. And so that's going to be B times, and what was the value for I1?
1 over 2A.
So that's going to be equal to B over 2A squared. So now I'm going to look at this and say, which one of those forms looks the easiest for me to use? And clearly the one that looks the easiest to me is to use the last form of B, the one that B is equal to 4A times square root of A over pi. So there I've substituted now for B, and we'll notice that we can simplify this some more. 4 divided by 2 is 2. I'm going to bring that 2 inside the square root, so that's going to become a 4 inside of the square root. And then outside I have 1 over A, right? A over A squared is 1 over A. Bring that into the square root, and that's going to be an A squared on the bottom. Clearly didn't need this big of a thing. A divided by A squared is 1 over A. And now I'm going to substitute for A. That's where I need the big square root. And so looking at A is M over 2KT, so it's divided by that, so 2KT over M. Four times 2 is 8. So it's square root of 8KT over pi times M. That's the average speed. Now, the way I showed it in class yesterday, I took that square root of 8 pi, and if we compare that to, or 8 over pi, if we compare that to what we had, come on, here, we had square root of 2KT over M. So that would be 4 times 2KT over, well, 4 over pi times 2KT over M inside the square root. And so I wrote this as that's the way I had it shown in class yesterday. So it depends on which way you want to look at it, what's the most convenient. And so I just calculated square root of 4 over pi, and that gave me 1.12, I believe it was.
1.13.
Okay, 1.13. So that was how I got the number in class. Yes?
Are we going to need to know all the different expressions for B and A? Do you know you're going to provide those?
You would neither have to know it nor have it specifically supplied. You would have to take, I'm out of time, so I can't do the RMS one. So I'm just going to finish with answering this question. You would have to take the equation. I would give you that equation F of B equals, and then I would give you the stuff that's in the box. And you have to figure out, now, which integral do I need to solve this problem? And based on that, how can I solve the integral The definition of capital B was simply to make my life easier so I didn't have to write a bunch of stuff. Right? So you don't have to use the capital B at all. Because the equations I'm going to give you have A in them, you will have to identify what A is to be able to use those equations. So what you'll be given will be what's at the top right corner only, that is this, plus the situation, like I said, like, find this, and then the equations that are in the box. That's what you'd be doing. Of course, the equations in the box would be in the equation sheet. Do you understand? Do you understand the mathematical steps you're going to have to take from that? Okay, we're out of time, but if you don't understand those steps, make sure you come by and ask, I'm not sure how we're supposed to plug something in. I'm more than happy to work through with you.